This is the lesson video for multivariable calculus for section 12.5, equations of lines and planes. And what we're going to do in this lesson is really try to talk about the geometry behind what's happening with the idea of finding the equation of a line and finding the equation of a plane and finding distances. So as opposed to just memorizing formulas, I want you to really be focused on why these things are the case. So this video might be a little bit longer, and I'm actually going to work through the majority, if not all, of these examples, because a lot of these things are going to be new to you, and they will be going through things in a way that you may not have seen before. So the first thing we're going to look at here is the equation of a line in three-dimensional space, and typically we use what's called the vector equation of a line. And most of you have seen this before in pre-calculus, but just as a refresher, when we find the vector equation of a line, we've got to have two things. Just like when we're dealing with the equation of a line, when we just have sort of, our standard point-slope form, we need a point and we need a slope. It's sort of the same idea here, except we need a position vector and we need a direction vector. The position vector is like your point, and then the direction vector is like your slope. So in this first example, it says, find the vector equation of the line passing through 1, 2, negative 3, and parallel to this vector 4i plus 5j minus 7k. Okay, so notice the equation that we have right here. So our vector equation of the line in this case, r, would be equal to, and I'm going to start with my initial position vector, and I'm just going to write this in the vector component form. So 1, 2, negative 3. Remember, that means I plus 2j minus 3k. And then I want to do plus t, where t is some parameter, and then I'm going to multiply that to my direction vector, which we know it's 4, 5, negative 7. So that's the vector equation of my line. Okay, so pretty straightforward. You've got a point and you've got a slope. So whatever I change for that parameter t, that's going to take me to a different point along that line. All right, so we can also go back and forth between the vector equation of the line and a parametric form of the equation. So this is where all that stuff we did on parametric equations starts to come into play, because we can break this apart into an x, a y, and a z component and look at those individually. And you can see here on this equation of the line that we had above, I can see that it would just be for the x component, I can see that I would have, the 1 plus 4t as the x equation. And then for the y equation, I would have 2 plus 5t. For the z equation, I'd have negative 3 minus 7t. So same idea, just writing it in a slightly different form and breaking those out into the x, y, and z equations individually. Okay, so once we've done that, we can also write what we call the symmetric equations of a line. And when we write these symmetric equations, basically what they are is just a way that I can show equivalency for that parameter t. So if you think about what we had up above here, we've got this equation for x. If I solve that for t, I get x minus x naught divided by a. Okay, so that's what this equation is. If I solve the y equation for t, I get y minus y naught over b, and then same idea with the z. And you can see they're all equal to t, so they'd all be equal to each other. So we call those the symmetric equations. Okay, so not difficult to do, just another way of displaying the same information. Okay, so what I want you to do on this problem, and I'm going to have you try this one, is find parametric equations and symmetric equations of the line that passes through the points a, 2, 4, negative 3, and b, 3, negative 1, 1. And this one's really simple, so I'm just going to have you work through it really quickly. So pause the video, find your equations, and then when you come back, I'll show you the solutions for it. Okay, and here's what you should have come up with. You can see that the main thing we have to figure out is, what is our direction vector? And so to go from A to B, you can see we went 1 in the x direction, 1 unit in the x direction, negative 5 in the y direction, and then 4 units in the z direction. So that's where all of these values came from that you see in my parametric equations. So you can see that 1 times t, the negative 5 times t, and the 4 times t. those came by getting that direction vector by finding how much did I change in each direction going from A to B. Okay, so pretty simple to do. All right, so let's take a look at another problem here. It says, at what points does this line intersect the XY plane? So if we want to know where does it intersect the XY plane, essentially what we're looking at here is Z being equal to 0. So that's what I need to be thinking about. Z has to equal 0 in this case. Okay, with that being the case, I'm going to use my symmetric equations. I had x minus 2 over 1 is equal to y minus 4 over negative 5. And if I plug 0 in for z, it gives me 3/4. So now where does this actually intersect? Well, I have two separate equations, right? I have x minus 2 is 3/4, and I have y minus 4 over negative 5 is 3/4. And what we end up with here is x is equal to 11/4, and y is equal to 1/4. So what's the point? My point would be 11/4, 1/4, 0, if you want to do a three-dimensional coordinate there. Okay, so not that hard to do. All right, so let's start looking at some things that are now going to get a little more complicated. This is still pretty straightforward, but we have to start thinking about what's happening three-dimensionally when we answer these questions. So we have two lines here, and you can see we have the parametric equations representing those lines. And it says, are the lines parallel? So the way that we can figure out whether or not these lines are parallel is by thinking about the direction vector for each one of these. And for the direction vector, we typically are going to use V to represent that direction vector. So for the first one, for line 1, my direction vector would just be 4, -4, 5. Okay, so remember I'm just using what's multiplied to that parameter t, and that's my direction vector. And then for the second line, I'll just call this one 1, and I'll call this second direction vector, vector 2. So this one would have components 8, -3, 1. So are these parallel? Well, you can tell if they're parallel if they're pointing in the same same direction. To be parallel, I don't care about where they are in space. I just care about what direction they're pointing. So if they were parallel, these two direction vectors would be scalar multiples of each other. And you can see in this case they're not, because the first component is multiplied by 2, the second one's multiplied by 3/4, the last one is multiplied by 1/5. So we don't have a consistent pattern there. So are the lines parallel? In this case, no, they're not parallel. So all we're doing is looking at those direction vectors to figure that out. So the next question says, do the lines intersect? Well, if I want to know whether or not the lines intersect, I would have to check, is there an intersection point? So remember, we're dealing in three-dimensional space here. So it's possible that these are what we call skew lines, meaning they're never going to cross. So what I'm going to do is I'm going to go through and I'm going to kind of use these equations that we have for L1 and L2 to try to figure this out. And I'm going to set up some systems of equations here. So first thing I'm going to look at are my x components. So I'm going to look at these equations. And when I do this, I have to make sure that, remember the parameter t is sort of going to be different for each one of these lines. So I'm going to call this T1 and this one T2. So when I actually set these equal to each other, I would say, is there a point where 1 plus 4T1 is equal to 2 plus 8T2? Okay, and then also I want to figure out at the same time, let's do the same thing for the y's. So remember, I'm going to use a T1 and a T2. Well, for the y's, I would be looking at 5 minus 4T1. And is there a point where that's equal to 4 minus 3T2? If these intersect, I should be finding a t value or t values that are the same in each of these scenarios. And I can find the t values, but then I also need to check, okay, we got the same t values potentially. Do we get the same z coordinate? Are they actually all hitting that the same z coordinate? Are we at that same point in space? So essentially what I've got here is a system of equations. So I've got If I rewrote this first equation, I would have 4t1 minus 8t2 is equal to 1. The second equation I could rewrite as negative 4t1 plus 3t2 is equal to negative 1. Okay, so a 2 by 2 system of equations. I'm not going to go through all the steps here, but you would get t1 is 1/4 and t2 is 0. Okay, so we got the t1 and the t2 values. So we can figure out for those parameters where they are in the x and the y positions. But in order for them to actually intersect, they have to have the same z position for that particular parameter. So now I'm going to check my z's. So when I check my z's, remember for the z's here, I'm just going to make sure that I denote that we're dealing with the z's. The first one is negative 1 plus 5t1. And the second z is 5 plus t2. Well, I know what t1 and t2 are. So here I would have negative 1 plus 5/4. And if these are going to intersect, that should be equal to 5 plus 0. Okay, so you can see that that's not the case. Those are not equal. So do the lines intersect? The answer would be no, they don't intersect. Here. So I would say no, and that's because the lines are skew. Okay, so again, I've got to have the x, the y, and the z all the same for those to actually be intersecting. Okay, so again, not super difficult, but again, every time you see these questions at first, it's going to be kind of new types of things that you have to be thinking about, and you've got to be thinking three-dimensionally what's happening here. All right, so let's get into equations of planes. When we talk about the equation of a plane, the equation of a plane involves the normal vector to the plane. And the reason it involves the normal vector to the plane is because we're going to be talking about dot products to derive the kind of standard form for the equation of a plane. So you can see that if I have a normal vector to a plane, any vector in that plane is going to be normal to that plane's normal vector. And you can see in this diagram kind of how that's the case. Well, what we're going to do here is we're going to look at two different vectors. We're going to have some vector r that's in our plane, and then we're going to have some initial position vector r naught. So we're going from, in this case, we're going from the origin to some point on the plane, and from the origin to a point that is going to intersect with a point that is the initial point for the normal vector. So you can see we've got x, y, z as sort of our kind of general point, and we've got x naught, y naught, z naught as that initial point for the normal vector. Now, if I had a vector that was normal to those, notice we can use r minus r naught as this vector that is drawn in here, this r minus r naught. So what we're going to do to derive the equation of the plane is we're going to use that idea of r minus r naught being perpendicular to that normal vector. Okay, so down below here, you can kind of see what happens. So if I took the dot product between the normal vector and that difference r minus r naught, I know I should end up with 0 because the normal vector is going to be normal to every vector in that plane. And obviously then in that case, r minus r naught. So we can rewrite it in a different form. And from that, once we know how to find that normal vector, we can actually go through and multiply all those components out and then combine everything over on one side of the equation. And I'm not going to show all the algebra there. But in the end, here's what we end up with using that idea. A times x minus x naught plus b times y minus y naught plus c times z minus z naught has to equal 0, assuming that our normal vector has the components a, b, c. And just like we talked about a minute ago, for that r vector and that r naught vector, you can see we used a general x, y, z, and then an x naught, y naught, z naught. So when you go through and you solve that dot product and get everything on one side and factor it out, this is what you end up with. So that's our standard form for the equation of a plane. Okay, so we'll use this a lot But keep in mind that there's a reason we're using that normal vector, and the normal vector shows up because that's how we're deriving this equation that we're using. We're using the idea that a normal vector to a plane is normal to, that vector is normal to every vector within that plane. Okay, so this next question is really simple. It says, find an equation of the plane passing through the point 3, -1, 7, and perpendicular to the vector, vector n. We typically use n for the normal vector, and it's 4 to -5. Okay, so all I'm going to do is essentially plug into that standard form. I know that I'm going to use the component of the normal vector that goes in the x direction or the I direction times x minus 3, because the 3, -1, 7 is like my x naught, y naught, z naught. Okay, then I'd have times 2 times y minus 1 minus 5 times z minus 7, and that would be equal to 0. Now, sometimes with equations of planes, you might see the 4 and the 2 and the -5 distributed through, and then you've got your x, y, z on the left side, or x, y, z parts on the left side, and then a constant value on the right side. All that is a simplified form of what we have here. The nice thing about this form, it's sort of like when you do the point slope form with equations of lines. If I have it in this form, I can see where that initial point is. I can see it's at 3, and this should be a plus. I just noticed it should be +1. But it should be at 3, -1, 7. That would be my initial point. If I multiply the 4 and the 2 and the -5 through and get the constant value on the right, I lose my reference to that point. So sometimes that point's important, sometimes it's not, but there would be a reason that we would leave it in that form, and it's because we want to be able to reference that point sometimes. All right, so let's look at this next question. It says, determine whether the planes 3x minus 4y plus 5z equals 0 and -6x plus 8y minus 10z minus 4 are parallel. Okay, so if these planes are parallel, we kind of want to be thinking about the fact that we know what the normal vector would look like for each plane, right? So what I'm going to do is I'm going to call this first one plane 1, and I'm going to call the second one plane 2. Okay, so I'm going to have a normal vector 1 that comes from plane 1, and you can just read them off if you have your plane written in the correct form. It's just 3, -4, 5. Okay, now let's look at normal vector 2, the one that is normal to plane 2. Well, that would be -6, 8, -10. Okay, so take a look at those two normal vectors and notice that normal vector 2 is a scalar multiple of normal vector 1. So essentially we have normal vectors that maybe they're pointing in opposite directions, but they're parallel to each other. So since they're parallel to each other, if you think about that from the plane perspective, if those normal vectors are parallel, that means that the planes also have to be parallel. So I guess the question was determine whether the planes are parallel. We would say yes, and the reason we know that is because vector n1 is parallel to vector n2. A lot of times with this type of stuff, I'm going to use sort of your geometric notation to save on my writing. So, you know, if you think back to when you were in geometry, you know, things like when you would write a triangle or when you'd write parallel lines or perpendicular, I use a lot of that shorthand notation to just avoid a lot of the writing. And you'll see that when you get into some of your higher math classes and you start writing out proofs, you're going to see a lot of that mathematical notation used. So try to get in the habit of writing with the notation when you can. Okay, so let's look at another one. So in order for us to define a plane, we have to know 3 points within that plane. So if all I have are 2 points, there's an infinite number of planes that can go through 2 points. But once I have a third point, that locks me into a single plane that would contain those 3 points. So if I want to find the equation of the plane, I'm going to need 2 vectors. So remember, we need to know a normal vector to get the equation of the plane. So I'm going to use the vector that goes through P1 and P2. So P1, P2, you can see the direction of that would be 1, 1, 2. Just getting how far did it change in the X, the Y, and the Z directions. And then I'm going to use P1 and P3. And I'm doing that because I have the same initial point. So you can think about the two vectors sort of lined up tail to tail. And now when I do a cross product, that's how I'm going to create that normal vector. So that's why I use the same initial point. So in this case, that would be at 2, -3, 3. Okay, so again, you've got to think about what we did in 12.4. When we do a cross product, think about your right-hand rule. Line up your hand with vector P1, P2. It would curl around towards vector P1, P3, and then that would create that normal vector sort of coming out of the plane, which is what we want. So I'm not going to show all the steps here, but I'm going to show you how we would find this. So we would do P1, P2, and we would do the cross product of that with P1, P3. And when you do that cross product, like I said, I'm not going to show all these steps, but you know how to do those steps. You would get 9i plus j minus 5k. So I wrote that normal vector in a different form just to kind of change it up a little bit. It doesn't really matter which form you use. Okay, so now we have our normal vector, and we can use any of these points in the plane that we want. They're all going to give us the same plane. Okay, so what I would do then is just go through and write the equation of my plane. So I can write it as 9, I'm just going to use P1 times x minus 1 plus 1 times y minus 2 minus 5 times z plus 1, and that would be equal to 0. So you might see it written in that form, and again, the nice thing there is we know what point we're looking at. Here, it doesn't really matter what point we're looking at. So if you check an answer on this, like if this were like a, let's say, a multiple choice question, or you work a problem in a book and you check your answer in the back, it might be written in that form. But really, since we could have used any of the 3 points, it probably, in this case, would be written in this form. 9x plus y minus 5z is equal to 16. Or I could say minus 16 is 9x plus y minus 5z minus 16 is equal to 0. But anyway, the equation of the plane is pretty easy to get, but it does involve getting a cross product. And that's part of the reason that we had a lot of practice with cross products, was because I want you to get to the point where you can set these up and solve them out very quickly. Some of you might be able to just look at this and do the cross product from there. And if you can, that's totally fine. I would actually encourage you to do it that way. If you can't and you need to set up your 3x3 determinant, go ahead and do that, whatever works best for you. All right, so let's take a look at another question here. And I included a diagram just so you can kind of see what they're talking about. It says, find the angle between the planes x plus y plus z equals 1 and x minus 2y plus 3z is equal to 1. Now, I've got a static figure here, so you can't really manipulate it. But remember, we can go into GeoGebra 3D, and if you want, you could graph these planes, and then you can kind of spin the thing around and get a good feel for this. But if we want to find the angle between the planes, what we can use as a method to find the angle between the planes is we can use the normal vectors to each of the planes, because the angle between the normal vectors is going to be the same as the angle between the planes. So that's all I'm going to do here is I'm going to say, okay, well, normal vector 1 clearly is just 1, 1, 1. And normal vector 2 is 1, -2, 3. Okay, so those are my two normal vectors, the vectors normal to those two planes. Okay, so once I've got that, now all I'm going to do is think about, all right, well, how do we find the angle between two vectors? Well, we can find the angle between two vectors by thinking about a dot product, right? So if I go through and I get the cosine of the angle between two vectors, that should be equal to the dot product of n1 and n2 divided by the magnitude of n1 and n2. Okay, and once we've done that, if you solve through all of that, I'll just tell you what you end up with is 2 times the square root of 42. And now we can find the angle. So our angle, if you wanted the exact value, it'd be the inverse cosine of 2 over root 42. I forgot my inverse here. Or that's approximately, if you want to really think about what that means, it's approximately 72 degrees. Okay, so that would be the angle between the planes. And when we're talking about that angle, obviously you could measure that in two different ways. We're typically going to use the acute angle as our measurement of the angle between the two planes. Okay, so the next question here, it says find symmetric equations for the line of intersection, which we're going to call L, of these two planes. So the same two planes, we want to find symmetric equations for the line of intersection. So you can see in the diagram how they intersect in a line. Okay, so what we have to figure out is how are we going to find that information? So to find that information, you know, when you're thinking about the equation of the line, we've got to have a point that is on the line. Okay, seeing how that line goes through space, I can choose one of my coordinates to be whatever I want. And if I can choose one of the coordinates, it makes it very, very easy to solve for the other coordinates. So using the equations of my planes, this is what I'm going to use. Okay, right now, if I just kind of use that and set those planes equal to each other, I would have, you know, 3 unknowns and 2 equations, right? So I don't have enough information to solve. So what we're going to do is sort of work around that by fixing one of those points to be something that we want it to be. And what I'm going to do is I'm going to say, here's something easy. Let's make z equal to 0. And if we do that, then the first equation just becomes x plus y is equal to 1. And the second equation becomes x minus 2y is equal to 1. So now I've got this 2 by 2 system, and I can solve that 2 by 2 system. And I'm not going to show the algebra, but you could do the algebra. You get x is 1, y is 0. And so from that, we know we have a point on our plane. Okay, 1, 0, 0 is a point on our plane. Or excuse me, a point on our line. So now we have a point on the line. The only other thing we need now is, remember, if we want the equation of the plane, we need a normal vector and we need a point. Well, we've got the point. So to get my vector, all I'm going to do is I'm going to take the cross product of normal vector 1 and normal vector 2. So those are the vectors that we were dealing with before up here. So I'm going to get the cross product of those two, and that's going to give me a vector that points in the direction of this line. Okay, so I'm not going to go through all the steps, but you can see we would use normal vector 1, normal vector 2. And when you work that out, this ends up as 5, -2, -3. So there's my vector that is the result. And then from that, I can get the equations of the line very, very easily, right? So I've got my direction, I've got my point. So you could write this out in a couple of ways. We could write it in the parametric form, or we can just write it as the symmetric equations, which is what they asked for here. I kind of ran out of space, so let me see if I can squeeze this in. So we'd have x minus 1 over 5 is equal to y over -2. And it's because it's y minus 0 over -2. And that's equal to z minus 0 or z over -3. So those would be my symmetric equations. Sorry, that 5 got a little scrunched there, but you get the idea. It's fairly simple to do. But the main thing is you have to be thinking about what's happening geometrically. And this is another one of those things, and I'm going to keep saying this. You want to get to the point where you can visualize this. If you can't yet, then you need to be creating 3D graphs of these things. Do it on GeoGebra 3D, get that 3D view of it, and you'll get a better feel for what's actually going on. All right, so the last thing we're going to talk about here is measuring distances. When we're measuring distances from a point to a plane. So there's actually a nice diagram in your book that shows where the distance from a point to a plane comes from. And the main idea is what we're doing is we're going to create a vector from some point on our plane to a point on the second plane. And what we really want to do is we want to be the shortest distance possible. And so if we were to take the scalar projection of that vector onto the normal vector, that would give us the shortest distance. So this formula that you see for the distance from a point to a plane, it's not just some random thing. It's a rearranged version of the scalar projection of a vector between 2 points, one on one plane, one on the other plane. So if I get that and then I project that onto my normal vector, then I can get the magnitude of that, and that will tell me what the distance is, that shortest distance, which is that perpendicular distance. Okay, so that's the formula that we're going to use. And like I said, if you really want to see it, take a look at it in the book. I'm not going to go through the whole derivation, but I kind of gave you the general idea of how it works. So I want to find the distance between this point 1, -4, -3, and the plane 2x minus 3y plus 6z is equal to -1. So to find this distance, it's not that difficult to do. It's really at this point just a matter of a formula. Now this is one where it probably makes sense just to memorize this formula, because you don't want to have to go through and try to derive this thing every time, because it's a little bit of a mess algebraically to work the whole thing out. So it probably makes more sense after you've used it 3 or 4 times, you'll have it pretty well memorized, but it probably makes more sense to remember this one. So my formula says ax1 plus by1 plus cz1 plus d divided by square root of a squared plus b squared plus c squared. So I want the magnitude of what was in the numerator divided by that square root. Okay, so pretty simple to do. You can see that my a is 2. That's coming from the equation of the plane. The x1 is 1. And then I want to add that to -3 is the b value times -4 plus c times z1. So my c would be 6. And my z1 is -3. And then the d value, it's a little tricky with the d value. So you have to remember that the standard form here is ax plus by plus cz plus d is equal to 0. So in our case, we have this -1 over here. If I think of it in the standard form, it's actually going to be +1. So I'm using a +1 because when I move that into the standard form, I've got to move that -1 over to the right-hand side, or to the left-hand side, I should say. Now in the denominator, it's just the square root of a squared plus b squared plus c squared. So we have the square root of 2 squared plus 3 squared plus 6 squared. And when I solve that whole thing out, I will end up with a distance of 3/7. Okay, so not difficult to do, very easy to mess up if you're not careful with your number operations there, but very simple in terms of a setup. Okay, so last thing I want to talk about here is finding the distance from a point to a plane, finding the distance between 2 planes by using the distance from a point to a plane. So what we're going to do here is sort of create the same scenario that we had by using the normal vector. So it says find the distance between these parallel planes. Okay, so first of all, I can tell these are parallel. If you look at the normal vectors that we have there, we've got 10, 2, -2. We've got 5, 1, -1. Clearly, the second plane has a normal vector that's just a scalar multiple of 2 of the normal vector for the second plane. Okay, so what I've got to do here is I've got to figure out a point that I'm going to use, because I want to use that distance formula that we just had. Well, I'm going to choose, again, something really easy, like we did on that problem a little while ago, and we said, let's just let z equal to 0. Well, what I'm going to do this time is I'm going to say, let's just let y and z be equal to 0. So y and z this time are 0. And I'm going to use this first plane. So plane 1 had the equation 10x plus 2y minus 2z is equal to 5, right? So if I say that y and z are both 0, that means that x has to be 1/2. So from this, x is 1/2, and that means that I've got this point 1/2, 0, 0, that's in plane 1. All right, so now all I've got to do is I've got to think about, okay, how am I going to measure this distance? Well, when I measure the distance from a point to a plane, remember I want to use the normal vector from the other plane. So it does matter which normal vector I choose. I'm going to choose the normal vector from the other plane. So when I do my distance formula, I want to make sure I'm using the distance from plane 1, which 1/2, 0, 0 is in plane 1, to plane 2. So my A, B, and C value are going to be determined by the equation of plane 2. So now my distance is just going to be the A value times 1/2 plus my B value times 0 plus, or actually minus my C value, or plus my C value, which is -1 times 0. And then the D value in this case would be -1 because I've got to move that 1 over to the other side. And that would be over the square root of 5 squared plus 1 squared plus 1 squared. I don't usually write the negatives when I'm going to square it anyway, but you could put -1 squared if you want. And in the end, when you simplify this down, this is root 3 over 6. Okay, so again, you've got to sort of think about what's happening geometrically when you solve these things out. And so don't blindly just plug into formulas, or when you run into problems like this one, you're not really going to be able to know what to do if you're not understanding graphically what's actually happening. Okay, so next time in class, we'll talk a little bit more about this. And like I said, more than anything, if you're having trouble visualizing, just make sure you plot these things in 3D and take a look at what's actually going on.